Hello everyone, I'm James Han, and this is my presentation for the Constant Velocity Lab. The goal of this experiment was to use real measurement to show that when the net force of an object is zero, the object moves at constant velocity, meaning it travels in a straight line at a steady speed. To do this, I recorded the motion of a marker moving across a flat surface, analyzed the motion using tracker, and built a simple computational model in closed script based on Newton's second law. My main result is the model's prediction lined up almost perfectly with the data from tracker, confirming that the motion can be accurately described as constant velocity. Fundamental physics principles. This lab is based on two of Newton's famous laws of motion. Newton's first law, sometimes called the law of inertia, says that an object will stay at rest or keep moving in a straight line at the same speed unless an outside net force acts on it. Newton's second law gives the equation F equals ma. It tells us that the acceleration of an object depends on the net force applied and its mass. If the net force is zero, the acceleration is zero, so the velocity doesn't change. That is exactly the situation we wanted to test when net force is zero. The object should keep a constant speed and direction. These are the preview of the result. Tracker data and closed script constant velocity model lined up almost perfectly. Formulas. The main formulas that we used was velocity formula, average velocity formula, position formula, Newton's second law. Final velocity equals initial velocity plus acceleration times time. Average velocity formula, velocity equals x over distance over time. Position formula, final position equals initial position plus average velocity times the time. Newton's second law, force equals mass times acceleration. Experimental procedure. To collect data, I filmed a marker rolling in a straight line on a flat surface. The camera stayed completely still, and I placed a ruler in the frame to calibrate the scale inside tracker. After recording, I loaded the video into tracker and carefully marked the marker's position frame by frame to create a table of position and time. This gave me a real-world data set that I could later compare to a physics-based model. So this is a tracker experimental video. Total time it took was 1.932 seconds. Initial position was 0. Initial velocity was 0.257 meters over second, and the total distance it traveled was 0.4 meters. This is computational model equation. I built a computation model in closed script. I set the initial position to 0 meters, the initial velocity to 0.257 at 201 meters per second, and set the net force to 0 so that the program would simulate constant velocity motion. The code used the same physics formula I mentioned earlier to calculate the predicted position at each time step. The simple model represents the ideal case of an object moving with no unbalanced forces. And this is the data that I got from the closed script. Comparing the data. By looking at this data, the closed script data and the tracker data, it almost lines up. The possible sources of error. Like in a real experiment, there were small sources of error. There could have been a friction. There was a friction and some air slowing down the object a bit. And also not clicking the exact spot every time in tracker, or the camera frame rate missing tiny bits of motion. Questions from the lab. What if the axes were flipped so that positive x and negative x were reversed? The numerical position and velocity values would simply change sign, but the shape of the graph would stay the same, and the conclusion about constant velocity would not change. To wrap up, both the experiment and computational model agree closely. This confirms that when the net force of an object is 0, it moves in a straight line at a constant speed, exactly as Newton's first and second law predicts. The simple lab is a clear demonstration of how fundamental physics principles accurately describe real-world motion, even with minor measurement imperfections.